So what is derivative? Derivative is instantaneous rate of change or slope of a tangent. But to fully understand what derivative is, let's go back to secant. Secant, or average rate of change. Let's look at it graphically. So let's say we have an xy plane, and this is x, and this is y, and we have some type of graph in this plane. So it goes, let's say, something like that. And we want to find average rate of change between 2 points. Let's say this is going to be, let's stick A in here, and let's stick B in here. So to find average rate of change, we have to take average change between f of A and f of B, somewhere around here. And as you can see, this line is actually going to look something like that between those 2 points. Now let's try to extend it a little bit. But this would be a secant line, and our average rate of change. So our average rate of change, ARC, will equals to basic slope formula, change in y over change in x. You guys should all know that from basic high school, whenever you learn that stuff. But in other words, I'm just going to rewrite ARC over f of equals to f of b minus f of a divided by b minus a. b minus a. Okay, so why do we care about secant line? How does it relate to tangent line? So for example, we want to find tangent line some point C over here. It's going to be around here. What average rate of change does, it actually approximates slope at this line. So for example, tangent slope of this line is going to be something like that. But as you can see, this is pretty decent approximation. But how can we actually find out exact slope of a tangent line? The way we do that is we just take points closer and closer to C. So let's say if we take a couple more points, and let's plot them out, and let's draw a couple secant lines. So from this point on, it's gonna look something like that. From this, which kind of, as you can see, actually gets even worse. But from this point, secant line becomes a lot closer to our tangent line than previously. The main idea, if you take 2 points very close to C, basically on C, secant line between those 2 points will almost perfectly approximate our tangent line. So if I just draw a line going this direction, and our secant line, as you can see, almost perfectly matches our tangent line. And this is basically what derivatives is all about. We want to find a secant line that gets so close to our tangent line that eventually it becomes 1. Now, for our purposes, we can basically take a point C, and we can just go one side from this C. So let's say C plus some very tiny number h, and h is approaches 0. It goes to 0. Now that we saw what calculus is all about, let's form a formal definition of a derivative. I'm going to redraw a graph so you guys can still follow it. Let's say, once again, this is x, y axis, and line is y equals x squared. I'm just going to make this as a line. As we talked about it before, if let's say if you want to find derivative at point A, so this is going to be f of A over here, f of A, and we want to take some number h, right? So if you take A plus h, and as you remember, h approaches 0, so therefore, like in this picture I'm drawing, there's significant distance, but we want to assume that h is so close to A that it's almost 0. But the point here, it's easier to illustrate it basically this way. But point here is going to be f of A plus h. Now that we have our framework, let's talk about notation for derivatives. It actually has a couple notations, but main one is dy dx. So this notation is actually very similar to change in y over change in x. As you guys remember, the basic slope formula. But I guess this is, notation implies that it's changed at a single point in time. Another notation for derivative would be f of x prime, which also implies derivative. Now, finally, actual equation for derivative is equals to f of A plus h minus f of A divided by A plus h minus A. As you can see, once again, our basic slope formula. Change in y over change in x. And as you can see, a's actually cancel out, and all we get is f of A plus h minus f of A divided by h. And this is our actual equation for a derivative. Now let's go through example of our function. So f of x is equals to x squared, and let's apply our derivative equation to our x squared function. So we have to plug in a plus h into x squared. So we get a plus h squared minus, now we have to plug in a into x squared, a squared, and divide this all by h, divided by h. After that, what do? We need to FOIL a plus h squared. So we get a squared plus 2ah plus h squared minus a squared divided by h. Okay, then as you can see, a squared cancel out, and this part cancels with this, and this h cancels with bottom as well. So all we get is 2a plus h. So this is basically our answer. But one thing you have to remember as well is that our h approaches 0, so this h becomes so small that we don't actually have to worry about it. So our overall derivative is 2a. So this is our final answer. So what are implications of all this? Let's say we want to find derivative f at x equals 1. Therefore, our derivative would be 2 times a, which is 1 in this case. And this equals to 2. Therefore, slope is 2. If we want to find derivative at f2 prime, slope would be 2 times 2, which equals to 4. As you can see, slope varies in our equation, depending on what value of x we have. This basically concludes my presentation. In my next video, I will talk shortcuts, how to find this derivative instead of going through this complicated equation. Thank you very much.